This video is going to be our introduction to the topic of Laplace transforms, and specifically about how we represent various functions and kinematic systems in control theory. Laplace transforms are going to be an integral element of that. When you look at most control theory resources, textbooks, papers, and things like that, what you're going to see are three different representations that come up frequently that are typically used in how people present or discuss these kinds of systems. So one of the ones that you've seen are the kinds of models that you see in MEC 228 and 328. That's where you're looking at differential equations and balance equations, things like that. Then those typically get translated into equivalent forms here, or these are equivalent's maybe too strong a word. They're certainly translatable between these two forms, but they just look a little different. The state space and vectors is what you saw last year in MEC 202 and 203. And that is where you have a model like x dot equals some matrix times x. So this is a vector equals a matrix times x, another vector. And the idea there is that you could then look at eigenvalues of A and learn some properties about the system, about stability, the kinds of solutions, and so on. But it's still a representation of the derivative of x in a nice, relatively simple form. We're actually going to jazz that up a bit when it comes to control theory, and we're going to add some other standard elements. And the main one is going to be this quantity called u here. So u, when you see it in a control theory paper, is the active control. And the idea is that something you are implying to the system, and we'll see some examples shortly that'll make this more concrete. But the idea is that this is a motor that you're turning on, or voltage through a heat generator, something like that, that you're applying to the system from the outside. Also part of this form is this AX, it'll be CX plus DU. This takes a bit of practice. If you're taking control theory a little later on, you'll see more of this. The idea here is x is the vector of the actual state. The challenge is you may not actually be able to know all the states. For example, you might have velocities in here that you can't actually measure, or it's expensive to measure. And y is going to be a vector of observed states. And it's actually pretty general. Lots of fun math there. We are going to pretty much take the y as the same as x. We're going to not worry about this. There's a whole fun thing about observability and controllability that you'll get into later. The key thing is that this package of the derivative of x, first derivative of x, with this matrix form here, sorry, this is typically represented as a matrix here as well. This form with ax plus bu defines the rate of change of x, and then there's some secondary variable y that can also be computed from x. That all comes together as the state space model for a system. And if you had a kinematics thing and it's linear, then you can represent your system in this way. It's guaranteed. An equivalent format that you're going to see more later, probably haven't seen yet, is the idea or the model based on a plant. So here it's more block diagrams coming in, coming out. And here we'd think of the same idea, but representing it as a plant. This is terminology that comes more from ChemEng, but it seems to be endemic in control theory, so just roll with it for now. Think of it as the mechanism or the physical system. And then that exports to your x of t. And again, there might be other things that come off of this, like if there is observability, if there's only some variables you can measure, you might have y of t coming out there. You might add feedback loops, things like that. But at the end of the day, you have some kind of control that you're applying. There's a plant. And what goes into this plant is typically represented as g of s. And this is equal to a Laplace transform somehow of the system. And we'll talk about that in this whole unit because we obviously haven't seen Laplace transforms yet. So this third peer, this third representation, is all based on Laplace transforms, so it becomes an important ingredient in any mechanical program to understand what that is. However, this will make way more sense, I think, if we look at some examples. So to start off with, let's look at the heating of a 3D printer tip. So 3D printers, you've seen, they expel molten plastics or other substances at the end of a tip here. And one of the crucial things is that the temperature be very tightly controlled at the tip. So for a particular material, you want to keep that tip at a specific temperature matched to that material. And of course, that involves turning on and off the heater in sequence to maintain that proper temperature. And the way that's achieved is that we have some kind of control. Here, let's call that we'll call it the current. In the heater, we control that. And what that does is it has an influence on the temperature. So here, X is equal to the temperature of the tip. The rate of change is dictated by some negative kx. This is the cooling law, Newton's law of heating and cooling. And it basically just says that whatever the temperature is, we're going to lose or decrease the temperature over time for a hot tip in a cold environment. And then this is saying, well, it's not just going to do that. We're going to actually add some current as well. And this B factor here is the effect of the current onto the actual temperature change or temperature rate. So this would be in something like amps, and there's some conversion factor that says, well, if I push this many amps through this heater, then what can I expect to have that result? Or what result can I expect in terms of the rate of change of the temperature? How fast will the tip heat up? Little common note here, X equals 0, you'll notice if we ignore the control, one of the things we often do is imagine what would the system do without the control. So take it back to the origins or the roots. And here we would have an exponential decay down to 0. And so typically we do this in control theory to make our lives easier, is we set X equal to 0 as not 0 degrees Celsius, but here would be the environment temperature. Why? Because all changes are going to be relative to that, and as long as the environmental temperature is relatively constant in a room, say, then that's a reasonable thing to make your baseline, and just makes the math easier. You don't have extra terms running around. Let's convert that. Let's put our control back in here and convert that to a state space form. So the state space form, we just go back for a page here and say, well, I just need to fill in these matrices here, A, B, C, D, and U. And it's actually really easy here because we just define our x vector as just a single value x. We only have one variable and one derivative here, so we're fine. And what we get from there is x dot is equal to a matrix, which is just negative k times x, plus a matrix, but it's a one element matrix times u. And then the y, which we don't really care about, we just want y equal to x. Again, this is a form that's standard, so we're just trying to model or manipulate our equation to look into that form. So we just do this. Here's our matrices A, B, C, and D for this case. And once we have those, that's enough information to fully define the system that we're talking about from the physics side. It just fits into the standard form that we can then work with, especially in Python, but also in theory. All right, so that's fairly trivial because there's nothing actually happening here. We just took all these components and wrote them out and pretended they were matrices. The plant is new. Again, you're going to see some examples of this when we get to the Laplace transform videos. But the essential idea is that if we rewrite this term here, let's do this, we get x prime plus kx equals bu. So that was another form that you would have seen for Mech 202, 203 models. We just put everything about the system on the left-hand side and leave the external things like the applied control on the right-hand side. And you can see there's a something plus k here. Anyway, you'll see there's some patterns that emerge from this. What this is going to turn into is a plant where we have our u function going in here, and this g of s that shows up in the middle is going to end up being s plus k for reasons that you'll see a little later on. This will be called the transfer function. I'm just laying this down here as an opener, We will fully explain how to do this and what it means as we go forward, but just so we have something concrete to put in this third form as we go forward. The key thing is we have the physics, that can lead to a state space, then we can get alternatively another form of the equation, just rewriting it a little bit, and that form will lead naturally to some other simple expression that we can use, and somehow this has some meaning. All right, let's do a couple more examples, and again, we'll skip over the plant because it'll be new. Let's go back to the classic physics model for a mass attached to a spring and a damper. We've got our classic F equals ma scenario here, so our ma, and we have our spring force, and we've got our damping force, and the same idea for the end here. We have our control, and again, that might be voltage applied to a motor, and then we're going to have a scaling factor that turns that into a force. So this is the dial that we control, so we put a dial on 2. Well, what does that translate into newtons? There is often going to be a scaling factor in between. That's what the B represents. If it's easier, we can also write things down in this form here, where we just moved all the x components to the left and kept the control force on the right. Now here we get into a bit of a problem because this is a second order differential equation, and second order differential equations do not fit this state space model immediately anyway, because this is strictly first order. We want first order with all these matrices. How do we do that? Well, fortunately, you actually saw this last year again. How do we do that? We define more variables. So the form I'm going to stick with is defining a w as a vector, and it's going to be a stack of x and x prime. And if there's two derivatives, I'm going to have x and the last derivative short of x double prime, so x prime here. So we're going to define that. And then we can rewrite this system as two first order equations. Let's see how that works. Then we're going to take the derivative and take the derivative of the w vector. Okay. So what does that look like? Well, again, we're going to take x and x prime, and we're going to take the derivative of both of those. Well, that's going to be a package of x prime and x double prime, right? Well, let's put these into terminology that goes with Python. So this is W0 here, and this is W1. Again, using zero indexing here. So if we have a vector W, whenever we talk about W0, it's the position. Whenever we talk about W1, the next thing in that list, it'll be x prime, or the velocity. And so here, what we can do is write x1 in terms of w, x prime in terms of w. That is w1. W1. And x double prime, oh, that comes from here. We're going to use that equation, and we're going to get 3x's minus 5x prime. But oh wait, we have names for both of those in terms of w's, because we want everything in terms of w's. So, a little more space here as well. 3x's, x's are w0's. Bracket. And then minus 5 velocities, minus 5x primes. Well, that's going to be a w1. Let's put all these in terms of blue if they're w's. This should be w1. My apologies here. There we go. It's x prime. And so this is an alternative representation for our system. In particular, we can go back and use that in an earlier example. As a parallel here, if we had x double prime with some u's on the end, well, what did that do? We just break it into different elements. We'd say let w equal a stack of x and x prime. And so the derivative of w, which would be the derivative of x and x prime, which will be x prime and x double prime, is going to equal, same as before, x prime is w1, and second derivative is this whole equation. We're just going to convert everything to the w, so x is w0, And then we have -5, not plus, -5 W first index, and then we'll break it into another piece here, and we'll call that 7 times U. Actually, I want to do this right too. We would write this as 0.7 times U. By the time we add up this second row completely, we're going to have what we had in our equation up here, x double prime equals some stuff. Here's all that stuff in that second row. And the first row is just capturing the fact that x prime is equal to W1. So through this process of starting with a second order differential equation, that's going to be our most typical case, and creating new variables, we can make a form that's going to work for us. So going back to the slide earlier, actually one more step here, we can take this and write it in matrix form. If we take our W vector, which is W0, square brackets here, and W1, this is equal to a matrix where we have none of the first one, 1 of the second, and then 3 and -5, and then plus 0.7 times U. That is equal to our, let's write this in vector form as well, W0 prime and W1 prime, or the whole thing prime, whatever. The idea is that we can break this down into a matrix times a vector. The derivative of our vector is a matrix times the original vector plus some control multiplier times our control function. And if that looks familiar, as it should, this is review from a while ago, but it is review, then we can see that in the state space expression here. So what we're going to do is do exactly the same thing. We're going to let W equal x and x prime. Won't belabor the obvious here, but W prime is going to equal some multiplier times W0, W1, which is position and velocity, and it's going to be exactly the same ingredients for the first row, because let's actually write this out on the left hand side as well. This is going to be W0 prime and W1 prime, and those are equal to x prime and x double prime. In the back of our minds, that's where this is coming from. So x prime is W1, that's fine. X double prime is all of this, so minus k times x. Well, W0 is x, so minus k here, minus c times the velocity. Well, we do our finger walking here. This will give us minus c times velocity. And then one last thing, we're going to have our b times u. But again, that only applies to the second derivative line here. The first derivative line is just saying the first derivative equals the first derivative in a twisted way. Here we would be 0 and b, and then times u. Now the only gotcha is, what if the mass isn't 1? So we actually have a mass here, so what we end up doing is dividing everything here in the differential equation line, the second derivative line here, by m. So that becomes a fully equivalent version of this, and we just throw in our y is equal to the identity matrix, say, times w plus 0 times u. That will give us the full form of our a times our vector plus b times our control, c times that, and d times that, to fit the state space requirements that you'll see as a standard form. Now the plant, again, we're not going to go into too much detail right now, but you can take from inspiration the last one. When I had this form written out, we ended with x prime plus kx. The derivative ended up turning into an s. The k with no derivatives ended up being itself. So it might not shock you to see that we have our control, we have our box here, our plant transfer function, and what's going to come out of there is our w's. Actually, this one's going to come out straight as x, as it turns out. X of t, and this g of s is going to look like, it's going to look like two derivatives. It gives us an s squared, but there's a mass multiplier One derivative gives us one s, and the k with no derivatives just gives us a k, no s's, or s to the 0. And so that is going to turn out to be an equivalent form to the matrix form that we have up top. Why? Again, we'll see. But there's some nice structure to this. It's not going to be a huge learning curve. Going from the physics-based model to the G of S form turns out to be fairly straightforward. Now, why is it important to have these things under your fingertips? Well, because imagine when we go to something like the double spring mass system, how is that going to work out? Again, this is a fairly complicated dynamic system, but we can break this down into a W vector, which here we'd have two variables to track. We'd have X and Y, and that means we would need X and X prime, Y and Y prime, and do the same work we did on the last slides, but it will be straightforward to just check down this list and go, every one of these terms is either an X or a Y or X prime or Y prime, so one of the W's, and with a multiplier. And then we can rebuild our system of equations. In fact, you can try to do this as we go along, but if we take a look at the state space for this, W prime is going to equal the, let's actually write this out because it's easier to keep that straight. So we're going to take the prime of the whole thing this time just for clarity. X, X prime, Y, and Y prime. That's going to equal X prime, X double prime, Y prime, Y double prime. And then we go here with our X, X prime, Y, and Y prime, and some matrix. And you can just go down the list here and see, well, what's X prime equal to? X prime is equal to this element. Well, that's 0 that, one of those, 0 and 0. Let's do the Y prime while we're at it. Y prime is equal to what times this? Well, 0, 0, 0, 1. That gives me a Y prime there, so those first and third lines end up equal. And then the second and fourth lines come from the math and the equations here. So here we have minus kx and another minus kx, so that's minus 2kx's. Well, the x is here, so minus 2k just goes in the first column. And same as before, we have to divide through by the mass. Then we also have some x prime components. We have a minus cx prime and a minus cx prime, so that's minus 2c's. But again, we divide through everything by the mass. And you can see, oh, this isn't so bad. Look for y's, we'd have a plus ky, so we just need a plus k over m here, multiplied by the third component, so the y, and last but not least, we're going to have a plus c over m here. Again, just taking this m and dividing it through by all the terms. C over m times y prime. And so if you multiply this out with your walking finger strategy, you're going to get this right-hand side up to the bux. We'll take care of that in a second. Y double prime is fortunately simpler. Let's start with the x. How many x's? Well, we have a kx positive, and again, it's going to get divided through by m. And then, sorry, this is assuming both spring constants are the same, both masses have the same mass, and both the damping coefficients are the same, just to make life a hint easier in this opening lecture. So k over m, how many x primes are there? There's x prime here with a positive c over m. Where are the y's? We're looking for the y's. Minus ky. And last but not least, y prime minus c. There we go. So there's some nice symmetries to this. There's these patterns in the first and third rows about being offset by 1. And in these ones, we have this nice complementarity that there's a positive and a negative, positive, negative, positive, negative kind of reciprocal nature there. And last but not least, again, there's different ways to represent this control depending on whether in our system we actually have the motor attached to pulling on this mass, or both. Maybe we have both. Let's pretend it's both for a second. So we actually have two things we can control. And so what we get out of that is let's do a column vector of ux and uy. Oops, ux and uy. And we're going to need a 4x2 matrix to fill in here to make the dimensions all work out. But the first row, x prime equals x prime, is already done. So I don't want to take any of ux and uy in that one. And the x double prime line, we're going to have x double prime equals blah, 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 plus b times ux. Okay. So that's going to be b times ux and 0 uys. So we do the multiplication there. If we multiply out this entire row and this entire row, we're going to recreate the equation that we had listed up there. And then the same pattern repeats itself for the third row. We have y prime equals multiply by y prime. Oh, that row is done. I don't want to add anything more to it. So I add 0 coefficients. And the last one is going to be the y component of u here times b. We need that term, so we put a b in the second column and 0 ux's to wipe it out. So this would be a state space representation of the double spring mass system damped and so on, with the extra ingredient that we'd usually have. Let's call this thing here w again. Y is equal to the identity matrix times w, just so these are the same, and plus the 0 matrix times ux uy square. This would be the last stage of this. And again, the only reason I'm emphasizing this is because this is going to show up in the code when we do Python stuff. So it's good to not forget that this is going to be part of the puzzle as we go through these kinds of modeling examples. All right. We will not go into the transfer function for this beast yet because we really need a little more theory before we can tackle that. But why do we have, what have we seen? We've seen that you can analyze kinematic scenarios for using all the state space balance equations, F equals ma, rotational torques, and all that stuff. And that leads you to models that are typically used when it comes to controlling those systems in terms of getting some analysis of the behaviors. So the state space vectors, we can talk about eigenvectors, and we can talk about stability. You'll hear that kind of phrasing, stability, used in those kinds of models. When you get to the plant block diagram and Laplace transforms, what you're going to hear are words like poles and zeros and frequency response, which should ring some bells from the Fourier section response. This representation is what we're going to be focusing more on. We'll be using this as sort of a check. But we're going to focus more on this because it ties into our earlier work of Fourier transforms and analysis, and also just because it offers what typically is, it seems to be more common to me in the analysis of control systems. This ends up being where most of the work is done and most of the representation is talked about, more so than state space. That'll all become more clear as we go through the class and the lectures, so for there we'll stop and get you into Laplace transforms.